should not be a problem. So apart from FM White, I'm using one more book. So I'll mention that today after I complete the discussion.
Thank you, sir.
Okay. Okay, it's now time. So let me start. Now, this link between the laws applicable to a control volume and the laws as applicable to a system, this is something you'll be using in a lot of places subsequently. So then it's important to get this part clearly. So we should understand that clearly enough so that even if we forget the final result, we should be able to quickly rederive the relation from first principles. So that is why let me do it by a simpler approach also. The simpler approach gives you the same result. It may not have the same level of generality, but then since the final result is the same, if the aim is to arrive at the final result, the shorter path should be helpful. That at some point, if you feel you're confused, you can go back and rederive it using a simpler approach. So all those surface integrals, etc., makes the previous derivation a little confusing. So then let's take a very simple example. That let's say this rectangular box is my control volume, and I have an inlet on the left hand side and an exit on the right hand side. And let me also make the simplifying assumption that velocity is and all properties are uniform across the inlet and across the exit. So in reality, the velocity will have a certain profile. But usually in most engineering calculations, we replace it by the average velocity. The average velocity is the volume flow rate divided by the area. So that gives you an average velocity. So here let us assume that it's the average velocity which is present throughout the inlet area, and similarly an exit average velocity is the velocity present throughout the exit area. So then my control volume is this. Okay. So our aim is to derive, if I have a certain property, capital B, which is the extensive property, and let us say it is associated with a value beta, which is the property per unit mass, the intensive value. And my question is, the rate of change of B for the system, because that we can, what is the rate of change of B for the system? That we can use our conservation laws to tell us what it will be. So since we are starting with thermodynamics, the two conservation laws here, the starting ones, are the conservation of mass and the conservation of energy. So we know that if I consider a system which has a fixed amount of mass, the mass in the system remains constant, rate of change is 0. So if I know the link between rate of change of mass for the control volume and for the system, from that I can then make a statement what the rate of change for the control volume would be. Similarly, the energy, we know that change of energy would be given by the Q added minus the W expended by the system. So to get that link, let us now consider the system, the arrangement at time t and at time t plus delta t. Now I know in the inlet pipe, the velocity is by assumption uniform and has a value of Vi. So now I don't have to bother about that cos alpha, etc., etc. I assume for simplicity that the velocity is at right angles to the inlet, which in most situations it will be. So then, if I ask the question that I choose the system such that the system will at both ends of the interval at t as well as at t plus delta t will occupy the entire control volume. So then my system, when I define, I must include the control volume. Now, if I consider only the time t, if I consider only this volume, that would be sufficient. But I want that even at time t plus delta t, it should occupy the entire control volume. In that case, what I do, I include in the system a volume which will flow in during the interval delta t. So during the interval delta t, if it is moving with velocity vi, whatever is in this cylinder with height vi delta t, if it is moving with velocity vi, this phase will reach this location in the interval delta t. So let me include this so that even at t plus delta t, the entire control volume will be occupied. So here I retain a portion which has length vi delta t in the inlet pipe. Now after and at this end, I keep the control volume, I keep the system boundary at the boundary of the control volume. So let me now follow it through time delta t. So in the time interval delta t, this would have moved in. Because by assumption, this uniform velocity is there in the pipe. So if this is moving with velocity vi, it will this entire phase will now reach here. So this is where the system would be. So if I see the system here is this. Now after time delta t, this phase has moved here. This phase has moved here. But what about this phase? It will move out with velocity ve, and in time interval delta t, it will cover a distance ve delta t. So the system boundary will now be this. So then let me put a hatching to just so that we can see clearly what the system is. So this is my system at t, and this is my system at t plus delta t. So it has flowed in at the inlet and flowed out at the exit. So B of system at T would be B of control volume at T plus beta at, so I have to take into account the B in this extra region. So it would be beta I. This is the value of B per unit mass, and the mass inside this would be the density into the volume. So rho I into the volume, that volume would be AI into VI delta T. So if your cross-sectional area here is AI, then it would be AI VI delta T. At delta T, I have to include the amount of B. So B is a extensive property. So the extensive property for if you divide the system into parts, the extensive property for the entire is the sum of the extensive property for the parts. So I'm adding for the control volume and the portion in the inlet or exit pipe. So now I have to include the value for the part in the exit pipe. So that would be similarly so this gives you in just a few steps the same relation which you would get if you assumed uniform flow and substituted in all those integrals which we derived earlier. Now let's relate this to mass flow rate. So at the exit, what is the mass flow rate? So if you see, that is the amount which has flowed out in time delta t. So the amount flowing out divided by the time. So that will give you the rate at which mass is flowing out. So the amount which flows out is the density into the volume which has flowed out. The volume which has flowed out was this volume. So that volume is AE into, so if this area is AE, that is AE into VE into delta T. AE is the area and VE delta T is the height. So the density into, so this much material has flowed out in time delta T. So what is the rate at which mass flows out? It is the mass which has flowed out divided by the time. So that would be similarly. So Vi by assumption is the inflow velocity. So it always this is the velocity with which it flows in. So Mi dot is also the rate at which mass is flowing in through the inlets. So Mi dot is also by definition a positive quantity. So then so this quantity here is same as this, which is Me dot, and this is same as this, which is Mi dot. You could write this also. BCB is actually beta over, sorry, beta rho dV. So this is the value of beta per unit mass, and this is the mass of an element. Integrate that over Cb.
Sir?
Yeah.
Sir, I don't understand the last equation.
Which one? This one?
Sir, previous. Sir, that,
This one.
yes, sir, please. Sir.
This BCV I have written as an integral. So this is the rate at which B changes in the control volume. So then B of CV is basically, it is an extensive property. So so for an element dV, the value of the quantity capital B would be beta into the mass of the element. So beta into the mass of the element is rho dV. This, if I integrate over the entire control volume, that will give me BCV.
Okay.
Yeah. So then the physical interpretation of this is so the system encloses a fixed amount of material. So then the rate at which B changes for the system is not just the rate at which B changes in the control volume, but the system also so the system continues to include material which has flowed out. So if you consider the rate of change in the system, it is not only the rate of change in the control volume, but it must add the rate at which B is associated with the material which has flowed out minus the rate at which B is associated with the material which has flowed in. So that is what these terms represent. And rate at which B flows so the rate at which B flows through an area, B is an extensive quantity, so it is the B per unit mass into the rate at which mass flows through the area. So that is what gives you these expressions. Now, coming to textbooks, the material I have taken here, it is discussed under the term Reynolds transport theorem in FM White fluid mechanics. but the derivation involving all those integrals, etc., that I took from STREETER. I was not familiar with this term Reynolds transport theorem. The reasons are plain because I studied thermodynamics from Van Wylen and Sontag, where this term is never used, nor is this concept used. And I studied fluid mechanics from Streeter. Streeter discusses the this same relation, but he doesn't use the term Reynolds transport theorem. But the derivation is probably one of the clearest derivations of this theorem. So this is from where I've taken it. Now, having discussed this, let's apply it, and let me start with the simplest, conservation of mass. And we'll do a problem. The problem is probably trivial, but that will help you to get familiar with how to use property tables. Now let me change to a new whiteboard, because as the whiteboard becomes larger and larger, scrolling through becomes slower. Now, if my extensive property is the total mass, sorry. So if my mass is the extensive property, the corresponding intensive property would be, what is the mass per unit mass? The mass per unit mass is unity. So therefore there is no beta in this expression because beta is unity. So this is what Reynolds transport would say for conservation of mass. Now the system by definition includes, I'm using system in the sense in which FM White uses it. In Zemanski's notation, that would be what is called a closed system. So such a system, the mass remains, the mass in the system remains the same because I am following a certain amount of fixed amount of material. So then this is equal to 0. Now, if I assume what I said earlier, so the properties as well as flow rates at any given point in space remains unchanged with time. So I have constant material constantly flowing in, material constantly flowing out. So if I follow the system boundary moves. But if I sit in one position and observe, the values don't change. So then if I integrate the density into the volume element for the entire control volume, at any point the mass does not change with time. So that value of the complete integral will also remain same. So therefore, in that case, which means if this also goes, then it will mean if I go back to my relation for mi dot that we had shown is and let me say so this tells you what we intuitively believe, that if I want to accelerate a fluid, I want V to increase from inlet to exit, correspondingly A must decrease. So this is what a nozzle would look like. So it has a certain VI here, it will have a larger VE here. And if I want to decrease the velocity, let's say I want to utilize its kinetic energy, then a diffuser would look like this. Now, if you look at books on the chapter on compressible flow, you will find that this is true for subsonic flow. So then for supersonic flow, you have a counterintuitive situation where the nozzle looks like this and a diffuser looks like this. So how is that possible? So the only way it can happen is that the rho overcompensates for the change in area. So for a nozzle, although area increases, the density decreases so much that the velocity has to increase. So therefore, if you want to accelerate a fluid starting from subsonic to supersonic speeds, the nozzle looks like this. So this is the subsonic section, and this is the supersonic section. Now, the mathematical justification of this would require detailed calculation of compressible flow, and as yet we haven't even done incompressible flow. So it is just to make you aware that this sort of a situation does exist. Now, let's take up a problem. The problem says steam enters a turbine through a pipe with a diameter of 150 millimeters. The inlet steam velocity is 90 meters per second, and the inlet pressure and temperature are 20 megapascal and 600 cc. So it says you have a turbine. In a turbine, the material expands. So if it expands, we normally show it in this manner, that the area increases. So in the inlet pipe, it says the diameter is 150 mm. The now properties of pure substances. We had mentioned this, that two quantities, two macroscopic properties are sufficient to specify the state of a pure substance in one phase. So for the steam, if I have specified that it's 20 megapascal and 600 degrees centigrade, that should specify the state of the system, and then all other properties, what is the density, etc. At the moment we require only density. Later we may require internal energy, enthalpy, entropy, etc. But those concepts we still haven't introduced. So at the moment we require density. So if we specify pressure and temperature, that should tell us what the density is. Now that is where we'll have to familiarize ourselves with property tables in order to determine what is the density at this pressure and temperature. Let's go further and see what is the value at the exit. The exit pipe of the turbine has a diameter of 600 mm. So since it has undergone expansion, so the diameter is 600 mm. And the exit pressure and temperature of steam are 300 kilopascal and 150 degrees centigrade. Assuming that the steam flows steadily through the turbine, calculate the following quantities: inlet steam density, mass flow rate of steam through the turbine, and exit steam velocity. So here we are given the pressure so it was 20 megapascal, now it is 300 kilopascal, which means it is 0.3 megapascal. So it has, the pressure has dropped. That is what happens in a turbine. So the pressure has dropped from this to this, and simultaneously it has also dropped in temperature. Why it will drop in temperature, that involves thermodynamics, which we have still not studied. So at the moment we'll take it as given that TE is 150 degrees centigrade. So then it asks, okay, it has used the so the book has used the symbols DI and DE. So the first question it asks is, what is the inlet steam density? So that is the question we had also raised, that we know the pressure, we know the temperature, how do we know the density? So the additional complication here is that steam can in principle condense. So how do we know whether condensation has occurred or not? So then what are the ranges of pressure and temperature over which the material remains as vapor? What are the ranges over which it is liquid? And what are the ranges and what is the a place where you can have both? So then better understanding of properties of water in its two phases. In most of our engineering calculations, which we'll do in this course, we are not really bothered about the solid phase. So there are situations where it's important, but the situations we'll be dealing with, working material in a turbine, working material in a compressor, those will if you see steam power generation, there the two phases we'll be dealing with would be vapor and liquid. So we'll not be worried about the solid phase. So let's just try to understand how do things vary as we vary the pressure and temperature. So then let us discuss if we take a certain amount of water and we heat it, and as we heat it, we keep on noting down what is the volume of the water. In that case, we can plot this on a TV diagram. So if we start with a liquid phase, as I heat it, as long as it doesn't evaporate, the volume expands slightly with temperature. But then the expansion is small compared to the original volume. So it follows a graph something like this. Then at a certain point, it starts evaporating. Then once it starts boiling, the temperature doesn't change, but the volume keeps on increasing. As more and more evaporates, the volume, the total volume increases. Finally, it reaches a point where the entire amount has evaporated, and beyond that, again it will undergo a slow expansion. So this is what the plot on a TV diagram would be for a certain value of pressure. Now, if I increase the pressure, in that case, evaporation we know will occur at a higher temperature. So the graph would come out something like this. So then if you plot it for various pressures, then we know that this is the point at which transition has started occurring, conversion has started occurring from liquid to vapor. And this is where it continues up till this point. So beyond this you have vapor, before this you have liquid. So if we plot such graphs for a variety of pressures, then all these points will be able to join where the phase change has started occurring and where it has ended. And then we'll get a boundary so this is the superheated vapor region. This is the and this is the so this sort of a region has a boundary like this. So then there is a certain pressure beyond which this phase change from liquid to a vapor, this is not clearly seen. It undergoes, instead of a sudden transition where a separation occurs between liquid and vapor phase, you see bubbles of vapor forming, and that continues until it finally becomes vapor. So then if you heat a certain amount of liquid, that is what we see at normal temperature, at normal atmospheric pressure, that you take a certain mass of liquid, you heat it, at a certain temperature it starts evaporating. So at atmospheric pressure it will start evaporating at 100 degrees. So it is as you heat it, it reaches here, then starts evaporating. It will keep on evaporating as long as material is present, and finally it will be vapor, and that you can heat further, and that is what gives you superheated vapor. Now, this sort of a transition will not be observed beyond a certain pressure. So if your pressure is higher than a certain critical value, in that case, the transition will be gradual. You will not see a sharp change in density. So that separation of liquid and vapor, that will not be seen. Its properties will change continuously. So the critical point, so this is called the critical point. Now, atmospheric pressure is approximately 0.1 megapascal. So that if you see that definition, the column of height of column of mercury, which balances atmospheric pressure. So multiply that by density of mercury into the value of G. So that will give you the pressure that you'll find is around 0.1 megapascal. So this is around 220 atmospheres. So that is, huh? Yes. Yes. What was your question? Okay. So the critical pressure is around 220 times the atmospheric pressure. So that is why in everyday life, we do not observe that phenomena of a gradual change from liquid to vapor without a boiling phase. So, but if you design your power plant to operate in that regime, then you have to take into account that this separation of liquid to vapor, this does not occur. So the design for the power plant becomes different. But at the moment, all we have to know is that there is this dome-like configuration on the TV diagram. So the portion within the dome represents the region where you have liquid and vapor in equilibrium. To the left, you have the subcooled liquid, and to the right, you have superheated vapor. Now, this is a rough diagram. Let's see what it is actually. So the TV diagram drawn accurately is this. So this is the dome. Here you have superheated vapor. Here you have subcooled liquid, and this is the liquid and vapor region, and this is the critical point. So I'll stop here because we have run out of time. In case you have any question, you can ask. Okay, then we'll close here.